Hi, this is Mrs. Villette, and this video summarizes the relationships between f prime and f. So we're going to look specifically at a graph of f prime, and we're going to try to answer questions about f from that. So the first thing that I want to do is mark off the important points on f prime, which are the zeros. So we've got zeros at -1, 5, and 15, and then the approximate location of the extrema. So my extrema are approximately, it looks like, at 9.5 is that high, 21.5, and I'm talking just about the x coordinates. So it's probably better that I actually mark those off on the x-axis. So I don't really care so much about the y coordinate of the extrema, just the x coordinate of the extrema. And then at approximately 1.5. So we're going to use those exact values of the zeros and the approximate locations of the extrema to answer questions about f. So our first question is the intervals over which f of x is increasing. Well, when we're talking about the intervals over which f of x is increasing, we're looking for where the derivative, which is the graph we have, is positive. We also need to approximate the endpoints of the domain of this function because we don't really know what happens outside of the interval. So let's go ahead and say that that endpoint is at about -2.5, and it looks like we stopped at 23. So just the stated intervals are what we can answer questions about this graph over. So the intervals where the function is increasing is anywhere that the derivative is positive. So from -2.5 to -1, and then -5 to 15. Again, we're talking about the y coordinates of this graph. So when we're talking about the function being increasing, we're talking about the places where this first derivative y coordinates are positive. So that corresponds with this interval here. And then if we want the original function to be decreasing, we are talking about the derivative's y coordinates being negative. So the derivative's y coordinates are negative between -1 and 5, and then again from 15 to the stated end of the domain, or 23. Part C asks us to find the coordinates of the local extrema and specify which ones are maximums and minimums. So our possible candidates are -1, 5, and 15. Those are the places the derivative is 0 and exhibits a sign change. At -1, my derivative goes positive, 0, negative, so that is going to be a local max. At 5, my derivative goes -0, positive, so that is a local minimum. And then at 15, it does the same thing as it did at 1. So a local maximum. Now we're looking for concavity. Concavity is related to the second derivative, so we're looking for places where the second derivative is positive, which means that the first derivative, this function, is increasing. So we'll take a look at this function, and we're going to highlight the places where that's increasing. So this is the reason that I found the maximums and the minimums. So there's really only a teeny tiny interval over there. So there's one big interval, and that interval goes from about 1.5 to 9.5, and then 21.5 until 23. Similarly, concave down, we are talking about where my first derivative is decreasing. And so I'll highlight that. My first derivative is decreasing from this left end of its domain to its local minimum, and then from its local maximum to its next local minimum. So our intervals where the function is concave down are just from the end of the domain, so -2.5, to the first local minimum, and then from the local maximum until the next local minimum. And again, those are just the x coordinates for the intervals of concavity. And then the last answer is the x coordinates of the inflection points. The inflection points are any places where the function changes concavity. So I can see that D and E share an endpoint of 1.5. That is where it changes from concave up to concave down. And then also 9.5 is shared between them, and 21.5 is shared between them. So the x coordinates, our changes in concavity, are going to be 1.5, 9.5, and 21.5. Notice that these are the x coordinates of the local extrema of f prime. So anywhere your derivative has a local maximum or a minimum, that is going to be the steepest slope of the original function, which is going to correspond to an inflection point. So when we think about an inflection point where we're changing concavity, it's that place where we have the steepest slope. So that's my inflection point. So this last page is just a summary of how to read a graph of f prime and have it tell you things about f. So notice this is a graph of f prime, and the notations on this graph are what the original graph f of x does on the indicated intervals. So if we first look at f prime as telling me when my function is going to be increasing or decreasing, we can see anywhere that my f prime is positive, so here and here, that corresponds to the original function being increasing. Anywhere my f prime is negative, that corresponds to places where my function is decreasing. Now there's a little spot right here where the f prime is not actually negative. That's where my f prime equals 0. But our test for increasing and decreasing said if there was a single place or a finite number of places where the derivative was 0, your function could still be considered to be increasing or decreasing on that interval. So just this one little spot doesn't change the fact that the function is decreasing on that entire interval. And then places where your derivative changes sign, those are your possible locations of your extrema. Notice that I didn't highlight this place where the derivative is 0, because even though the derivative is 0, it doesn't change signs. The function is decreasing on that entire interval. Okay, now we've pointed out the locations of the extrema. Now we just need to look at the fact that the original function goes from increasing to instantaneously doing nothing to decreasing, and that makes us a local maximum. Similar, the original function, the derivative is negative, so it goes decreasing, 0, positive, and that is a local minimum. Sometimes helps just to draw those situations so that you can tell what type of extrema you have. Okay, the next thing we're going to look at is the slopes to the derivative rather than the derivative's y values itself. So we take a look at this graph, and it's still the same graph. It's still the graph of f prime, but now we're going to be looking at information about when this function is increasing or decreasing. So right here, this function, the derivative is decreasing, and then also here, and then it is increasing here and here. Now anywhere the original function is concave down, the derivative will be decreasing. So here's my derivative, it's decreasing, my original function is concave down. Here's my derivative, it's increasing, the original function is concave up. Derivative is decreasing, concave down, derivative is increasing, concave up. Now anywhere you see those two colors intersecting, so you're changing from concave down to concave up, that's going to be a point of inflection. So we have 3 places where we have those points of inflection. So the last thing I'm going to do is go ahead and take this derivative function, and I am going to try to sketch what the original function looks like. So we are going to start at just some arbitrary y value. My original function, the derivative is positive, which means it's increasing, but then my derivative, it is itself decreasing. So my original function is increasing but concave down. I'm going to go ahead and make some marks here at the important places. So anywhere my derivative is 0, that's going to be important. And then anywhere my derivative has a local extrema, that is going to be important. So those are going to reflect our possible maximums, minimums, saddles, and inflection points. So going back to what we think the original function does, I'm going to go ahead and change this to blue. So the original function is increasing but concave down. So increasing concave down. Now we are still concave down, but we are now decreasing until we get right here. And that was an inflection point. Now we look at my derivatives are negative, so my function is decreasing, but my derivatives are increasing, so I am now concave up. So now I'm going to go concave up, but still decreasing. Okay? Now we look here, and my derivatives are decreasing and negative. So that means that we are going to be concave down, but decreasing. So concave down and decreasing means that. So notice this place was a saddle point. That was a place where my derivative was 0, but didn't change sign. So it kind of looks like the bend of a cubic function. Okay, and I may have run myself out of room. I probably should have started a little bit higher, because now my derivative is still negative, so I'm still decreasing, but I should be decreasing concave up here until 4. So decreasing, but now we are concave up, so that was another inflection point. So decreasing concave up until right here. And then I am concave up because my derivatives to this function, my derivatives are increasing, but now my derivatives are positive. So my original function is increasing until right there, which is possibly another location of an inflection point because that looks like it is a local extrema. So our inflection points are, let's highlight them in red, they are the places where my derivative had local extrema. And then our local maximums and minimums we'll highlight in green. Those are the places where my derivative was 0 and exhibited a sign change. Now, one thing that you notice, it was sort of arbitrary where I started here, and I almost started to run out of room. If I were to just shift this entire function up here and follow that same path, that would still be an acceptable function because all we're measuring with the derivative is the slopes, not the y values. So for example, I could have a function that looks something like this, not an exact duplicate of what I did, but the same basic shape, and that would still be an acceptable version of my function f.